Linear maps are quite abstract things, so it can be helpful to have a way to make them more concrete. We're going to do that in this video by introducing the concept of a matrix of a linear map. So here's the motivation. Let's say you've got a linear map T from a vector space V to a vector space W, and you choose a basis V1 up to Vn of V. Now, if you know T of the VI's for each I between 1 and n, then you can work out just from that information T of V for any element V in the domain capital V of T. And the reason for that is that that basis is in particular a spanning set. So any such vector lowercase v can be written as the linear combination AI VI, and then if you apply T to V, that's the same as applying T to this big sum, and of course, as we've seen a few times, you can now move T through that sum, and you get AI times T of VI. So knowing just the T of VI's, you can work out T of V for any vector, little v and big V. But even better than this, let's suppose you have another basis, W1 up to Wm, of the codomain W of T. Then every W in big W, and in particular these vectors T of Vi, can be written uniquely as a linear combination of the W's. That means we can completely describe a linear transformation T from V to W by choosing a basis for V, choosing a basis for W, and writing down the scalars Aij such that T of Vj is the sum over I of the Aij's times Wi. Those scalars are going to make up what we'll call the matrix of the linear map with respect to the basis consisting of the V's for the domain capital V and the basis consisting of the W's for the codomain capital W. So here's our formal definition then of the matrix of a linear map. You take a linear map T from V to W, you choose a basis which we'll call B of V and another basis C of W. You then define some scalars Aij by T of Vj being equal to the linear combination sum from I equals 1 to n of Aij Wj. Then the matrix of T with respect to initial basis B and final basis C, which we write like this, is defined to be the m by n matrix whose entries are these Aij's, so the scalars that you need to express T of Vj in terms of W1 up to Wm. So some remarks on this definition, two remarks on this definition. First of all is that we use a slightly different terminology when we're thinking about linear map from a vector space V to itself, and where we use the same initial and final bases. So if we have a linear map T from a vector space V to V, and if curly B is a basis of V, then we sometimes say the matrix of T with respect to B just to mean to the matrix of T with respect to initial basis B and final basis B. And finally, a remark on the interpretation of this matrix. The jth column of the matrix of T with respect to initial basis B and final basis C records the scalars that you need to express T of Vj as a linear combination of W1 up to Wm. And that's the easiest way to remember what's happening when you're working with matrices of linear maps, and the easiest way to work them out. You can work them out column by column by working out T of each basis element in the initial basis, expressing it in terms of the final basis, and writing the coefficients you use in the columns one by one. So let's see an example of doing this. We've met this linear map before. It goes from r squared to r cubed, and the rule for this linear map was that T of a vector xy was equal to 2x plus y, and then 0, and then x minus y. If we wish to work out a matrix for this linear map, we have to choose bases for the domain and the codomain, so we'll choose the standard bases in both cases. So we'll use the standard basis b of r squared and the standard basis c of r cubed. And I'm going to put some primes on here, so these just mean the standard basis vectors. For example, E1 prime refers to 1, 0, 0, and E2 prime is 0, 1, 0, and so on. I'm just putting the primes there so we don't have E1 and E2 meaning two different things at the same time, because that will be confusing. So if we want to work out the matrix of the linear map T with respect to initial basis B and final basis C, then what we have to do is compute T of E1 and T of E2 and express those things as a linear combination of the basis elements E1', E2', E3'. And the scalars that we use will be the entries of the columns of the matrix of T. So let's work out T of E1. T of E1 is T of 1, 0. Substituting x equals 1 and y equals 0, we get 2, 0, 1. And now we need this as a linear combination of the basis elements of our final basis C. And of course that is 2 E1' plus 0 E2' plus 1 times E3'. So we can write those into the first column of our matrix. It will go 2, 0, 1. Now let's work out T of E2, which will tell us what goes in the second column of this matrix. T of E2 is T of 0, 1, and substituting x equals 0 and y equals 1, we get the column vector 1, 0, minus 1, which is, in terms of the final basis C, 2 times E1' plus 0 times E2' minus 1 times E3'. So this tells us the second column of our matrix. It tells us the second column is 2, 0, minus 1. And that is the matrix of the linear transformation T with respect to initial basis B and final basis C. As a side note, it now becomes clear why we had to use sequences for our bases. It was important what order the bases came in, because the order that the basis comes in tells you the order of the rows and columns in the matrix of a linear map. If our bases were just sets and not sequences, then they don't come in an order, so we couldn't do this kind of thing. So the reason that we need our bases to be sequences is so they come in a fixed order, so we know how to write down our matrices of linear maps. Let's now work out another example. This is another differentiation example. We will take D to be the linear map from r less than or equal to 3 of x to r less than or equal to 3 of x. And you'll remember that r less than or equal to 3 of x means the vector space consisting of all polynomials in one variable x of degree at most 3 with real coefficients. As usual, D will be the differentiation map, so d of f is df by dx, and B will be the basis of the codomain, or the domain, consisting of 1x, x squared, and x cubed. So what we're looking for is the matrix of D with respect to the basis B. In other words, the matrix of D with respect to initial basis B and final basis B. And in order to do that, I have to work out D applied to each of these basis elements in turn, and those will tell me what the columns of the matrix are. So let's do them. We'll begin with D of 1. Well, D of 1 is the derivative of the constant polynomial 1, which is 0. But I'm going to write this 0 in a particular way. I'm going to write it so I can see the coefficients of each of the basis elements. So that's 0 times 1 plus 0 times x plus 0 times x squared plus 0 times x cubed. That tells us the coefficients of all of the elements in my basis. So my first column records what happens to the first basis element. It records the scalars we need to express D of the first basis element in terms of our basis, and those scalars are 0, 0, 0, and 0. Let's do the next one. What's D of x? D of x is 1. And again, I want to emphasize that we need to express this 1 in terms of our basis. And we can write that as 1 times 1 plus 0 times x plus 0 times x squared plus 0 times x cubed. So our second column will be 1, 0, 0, 0. So remember what's going on here. The rows are labelled by basis elements. And those are basis elements for the codomain, and the columns are represented, the columns are labelled by basis elements for the domain. in our case, the domain and the codomain are the same, and we actually use the same basis for the domain and the codomain. So I've got the same labels on rows as I do on columns, but in general that wouldn't be true because you'd have a different basis for the domain as you would for the codomain. Okay, let's keep going. We want d of x squared. d of x squared is 2x, which is 0 times 1 plus 2 times x plus 0 times x squared plus 0 times x cubed. So let's just put that in. So that tells us the third column is 0, 2, 0, 0. And finally, let's do d of x cubed. That's 3x squared. I'm not going to write them all out this time. This is 0 times 1 plus 0 times x plus 3 times x squared plus 0 times x cubed. So there is the matrix for our linear map D with respect to the basis B. Finally, we're going to think about some matrices for the identity map. So let's say you take the identity map from a vector space V to the same vector space V. And let's say you also take any basis curly B equal to B1 up to Bn of V. Then I claim that the matrix of the identity map with respect to the same initial and final bases is always the identity matrix. And the reason for that is just that if you think of what is ID of B1, well, that is B1. So that's 1 times B1 plus 0 times B2 plus 0 times B3 up to 0 times Bn. And that tells you the first column of this matrix is 1, 0, 0, 0, 0. And that's the same as the first column of the identity matrix. So let's write this down. ID with respect to initial basis B, final basis B is rows are labelled by the basis we're using for the codomain, which is B1 down to Bn. Columns are labelled by the basis we're using for the domain. Again, that's B1 up to Bn. And we've just seen that the identity applied to B1 is B1 again, so the first column, I'll do this in a different colour, is 1, 0, 0. Okay, let's think about the next basis element. The identity applied to B2 is B2, and that is 0 times B1 plus 1 times B2 plus 0 times B3 plus 0 times B4, all the way up to 0 times Bn. So the second column, the B2 column, is 0, 1, 0, and then lots of zeros. Okay, and you can see what's happening here. If we keep going with this, we end up with this matrix, which is exactly the identity matrix. So we have demonstrated my claim that the matrix of the identity with respect to the same initial and final bases is the identity matrix. But the matrix of the identity map with respect to different initial and final bases is never the identity matrix. So let's look at an example of working out the matrix of the identity map with respect to two different initial and final bases. So we will take the identity map on R squared. We will take our initial basis B to be the basis 1, 1, then 1 minus 1. We've proved several videos ago that that really is a basis of R squared. And we will take the final basis, we'll call this curly E, and this will be the standard basis. So as usual, E1 means the first standard basis vector, 1, 0, and E2 means the second standard basis vector, 0, 1. Let's work out this matrix. So if we want the matrix with respect to initial basis B and final basis E, I have to do my linear map to each of the elements of the basis B in turn and express them in terms of the final basis, curly E. So here is the identity applied to the first element of my initial basis B. That's the identity of 1, 1. Well, of course, that's just 1, 1 again. And 1, 1 is equal to 1 times, 1 times E1 plus 1 times E2. So here, let's write these in again. We have the rows labelled by the basis for the codomain and the columns labelled by the basis for the domain. And the first column tells me how to express my linear map, which in this case is the identity, applied to the first basis element for the domain, which is B, so the first element of the initial basis. So here we got 1e1 plus 1e2, so that first column is 1, 1. Next, let's work out our linear map applied to the second basis element for the domain, so the identity applied to 1 minus 1. Of course, that's just 1 minus 1 again, and of course that is e1 minus e2. So 1e1 plus minus 1 times e2. So the coefficients are 1 and minus 1, and we write in 1 and minus 1 for this basis of the identity. For this matrix of the identity with respect to initial basis B and final basis E. So I hope it's clear that when you are finding the matrix of a linear map and the final basis that you're interested in is the standard basis, it's always going to be really easy to work out these coefficients, because whatever vector ABC you get, that's just A times the first standard basis vector plus B times the second plus C times the third standard basis vector. So when the final basis is a standard basis, it's always easy to work out these matrices. But it could be harder if we wanted the other way around. For example, what about the matrix of the identity with respect to initial basis E and final basis B? Now this one's harder because you now have to work out how do I express E1 in terms of the final basis consisting of 1, 1 and 1 minus 1. So you have to do some work to work this one out. Or at least it seems as if you have to do some work. But in fact we're going to see a connection between these matrices here, which will enable us, at least in general, to work this out in a slightly easier way, and in fact to get some information about the relationship between those two things.